Today we're going to learn about something, a game called Who Will Win the Last Banana. You should have just watched a video on, it was like a YouTube video about a game called Who Will Win the Last Banana. And in this game, each player rolls a die. So if there's two people playing, both people are going to roll the dice. So here's two dice, roll them. And it doesn't matter who rolls which number, you just look at the numbers. So if the highest number is a 5 or a 6, which in this case the highest number is a 6, that means player 2 wins. If you roll the dice and you got something like this, that means the highest number is a 4, so player 1 would win. So what I want you to do first is think about, just think in your head, do you think that either player has an advantage in this game? For example, if you were playing this game, would you rather be player 1 or would you rather be player 2, or does it not matter? So take a minute and write down your best guess and explain your choice. Player 1 because, player 2 because, or it doesn't matter because. Okay, pause the video a few more times. Otherwise, now what I want you to do is actually play this game with your partner. So you're going to have to split off into groups of 2. You have to just have 2 people to play this game. So if you have to move to a different table to play real quick, that's fine. But you need groups of 2. If there is like one left over, maybe the teacher can pair up with somebody, but you need groups of 2. And then what you're going to do is you're going to gather some data to kind of either confirm or not confirm your choice up here for number 1. So you are going to play this game 20 times with your partner. So you're each going to roll the dice once, and looks like it's a 5, so player 2 wins. So you're going to put a tally under player 2. Then you're going to play again. The highest number is a 6, so player 2 wins again. Every time the highest number is a 5 or 6, player 2 is going to win. Every time the highest number is a 1, 2, 3, or 4, player 1 is going to win. You might want to put like one of your names up there. So you could be like, player 1 is Mrs. Grinwis, player 2 is Mrs. Grinwis's partner or something. So you can keep track of who's who. And then you guys are going to play 20 times. Record the tallies there. Right below in the table, find the percentage of wins. So however many you won out of 20. And then answer A and B right below that. And then, pause the video and you can do that. And then we'll come back together. Go for it. Okay, so hopefully you guys had a chance to play the game. When I played this game with somebody, I got this data right here. So 8 out of the 20 times player 1 was the winner, and 12 out of the 20 times player 2 was the winner. So that means that there was a 0.4 probability of player 1 winning and a 0.6 probability of player 2 winning. This right here, I want you to notice that these probabilities right here, they add to 1. Whenever you have probabilities that completely encompass all of the possible outcomes, all the probabilities of those things have to add to 1. So in this game, either player 1 wins or player 2 wins. There's no middle ground. There's no third option. So those 2 options encompass all of the possible outcomes, which means that when you add the probabilities of those, they should all add to 1. So just kind of make a note of that is what happens here. Now, in your situation with you and your partner, player 1 might have won more often, or player 2 might have won more often. For me, it was player 2 that won more often. So the question is do you think this is good evidence that player 2 is always going to win more, or did this just happen when we play this game 20 times right now in our group? So what we need to figure that out is we need a lot more data. So what we're going to do as a class is, if it were normal and we were doing this together as a class, we would all pool all of our data together to answer the next questions. However, that's kind of complicated to do on a video, and I need to be able to talk through the rest of this video with numbers. So let's just pretend that we pooled all of our data together, and if each group played 20 times, and we'll say there were maybe 13 groups playing, that means that there were 260 little rounds that were played between the whole entire class. And let's say that of those 260 rounds, player 1 won 113 of the 260 times, and player 2 won 147 of the 260 times, which gives us these percentages right here. Before we go any farther, I want to point out that not only do these two probabilities add to 1, we can also say that these two probabilities right here are complements of each other. Not complements like, hey, I like your pants, but complements like they couple with each other, okay? So if we think of player 2, the probability of player 2 winning. So this right here, this like P and then a parenthesis and then 2, looks kind of like function notation from back in algebra. It's not. This is in here, in this unit, it's probability notation. So this is the probability of player 2 winning. That equals 1 minus the probability of not 2 winning. Or like 1 minus the probability of player 1 winning. So it's like 1 minus the 0.43 gives you the 0.57. Now, there's a special notation for complements. Instead of the probability of not 2, we can say the probability of 2 and then a little c up there. That means not. Okay? So probability of not 2 means the same thing as probability of not 2. That c means not. It's like the complement of 2, which is not 2. All right? So there's an idea just that these two are complements of each other, because you could think of the probability of player 1 winning as also the player probability of not 2 winning. Those are the same thing. So now these right here, everything we did in class, these are all considered experimental probabilities. So I want you to, on your paper, mark all of this, and we're going to write experimental probabilities. Okay? Because these are probabilities that we got from doing the experiment, from actually gathering actual data in the world. We actually played the game. These were the results. Now, experimental probabilities are not always representative of the true probability. As you do this more and more and more and more and play more and more games, it's going to approach the true probability, just like my free throw percentage at the beginning was all over the place. But then as I shot, closer to 80 free throws, it started kind of zeroing in on my probability, like the true probability. Same thing here. If we played 1,000 games or 10,000 games, it would definitely get closer and closer. We could make a pretty good estimate of what the true probability is of us winning. However, these are not necessarily the true probability. These are experimental probabilities. This is like the actual raw data that we got. Now, if we want to determine the true probability of player 1 winning, we're going to make what we call a sample space. A sample space is where we list out every single possible outcome of playing this game. And then we actually find out how many of those outcomes have player 1 winning and how many of those outcomes have player 2 winning. So when we do that, we are going to make a table that looks like this. So at this point, you might want to pause the video and take a minute to write these down. Basically, along the top is, this is what one of the dice rolled. Along the side, this is what the other dice rolled. So you could both roll ones. You could roll a 1 and a 2, a 1 and a 3, 1, 4, 1, 5, 1, 6. And then the first dice could now be a 2, and the second dice could now be a 1. It's important to note that these two are actually different outcomes. Okay, this is like if you had a red dice and a blue dice right here. So like red was 1, blue was 2. This would be the other way. Now, red was 2, blue is 1. So those are counted as 2 separate outcomes. So go ahead, take a minute and fill out that whole table. Pause the video if you need to. Okay, now that we have our whole entire sample space filled out, now we want to figure out what is the probability that player 2 is going to win and what is the probability that player 1 is going to win. Now, player 1 wins if the largest value is a 1, 2, 3, or 4. So in this table, that's happening in these spots right here. Okay, in those spots, the largest value is a 1, 2, 3, or 4. That means that there's no 5s or 6s. Okay, now all of these spots have 5s and 6s. So in these spots, player 2 would win. So the probability of player 1 winning is going to be 16. There's 16 boxes highlighted in pink here, 4 by 4. 16 out of the total 36. So 16 out of the 36 is 4/9, which is 0.4 repeating. So the probability that player 1 is going to win is about 0.44. And then down here, it says which was closer to the true probability you found, in 4A. Your group data or the class data, why do you think that is? And I said, well, when I did this with just my partner and I got 0.4. When we did the class data, I got 0.43. And 0.44 is the true data, which means the class data is closer, and that makes sense because the law of large numbers says that the more games you play, the closer the probability will get to the true probability. These right here, like this right here, is called a theoretical probability. Okay, the theoretical probability is the true probability. Whereas the experimental probability is what we actually got when we played, may or may not be true. It'll likely be a little bit off. Maybe also make a note that this thing right here is called a sample space. And it is a list of all possible outcomes. And once you have that written on the back, we're going to talk about the important points of the day. So some important things that we learned today is, well, I'm going to kind of tell you now too, this idea of a probability model. We didn't really talk about that a lot, but it is a list showing all the possible outcomes and their probabilities. This is an example of a probability model. Okay, it's possible in this experiment for people to have 1, 2, 3, or 4 or more children. And here's the probability of each of those. Okay, so this is called the probability model, listing each possible outcome and then the probabilities that go with it. In a probability model, all the probabilities must add to 1. So if you were to add up these 4 numbers, it should equal 1. And each probability is in between 0 and 1. We don't have any negatives, and we don't have anything bigger than 1. The complement we talked about is the probability of an event not happening. And the probability of not A is the probability of 1 minus the probability of A. So for example, if P of A equals 0.7, then P of not A must be 0.3. Mutually exclusive is, that means events that cannot occur together. So for example, in our game, those are mutually exclusive. Either player 1 was the winner or player 2 was the winner, not both. And then the general addition rule is sometimes called like the OR rule. It's the probability of A or B, and it just means you add up the two probabilities. So probability of A plus the probability of B, but this only works if they're mutually exclusive, which means there's no overlap. Okay, so take a minute and write all of this down. Pause the video if you need to, and then we'll go on to the check your understanding. Okay, so hopefully you have all of that written down. If you don't yet, pause the video and finish it up. Otherwise, the Check Your Understanding says Pew Research Center reported that among mothers, family size is shrinking. Suppose we are to randomly select one mother, aged 40 to 44, and record the number of children she has. Here is a probability model. So if we select one mother, the probability of that mother having one child is 0.22. The probability of them having 2 children is 0.41, 3 children is 0.24, and 4 or more children is 0.13. So take a couple minutes and answer A, B, C, D, and E. Try your best. You can talk with your group if you want, and then we'll come back together in just a few minutes and talk about these together. So pause the video here and take a minute to do those. Okay, so this is a valid probability model because each probability is in between 0 and 1. Okay, they all are, and they all add up to 1. That plus that plus that plus that all equals 1. The events have one child and have 2 children are mutually exclusive because you cannot have exactly one child and exactly 2 children at the same time. They cannot occur together. Either you have 1 or you have 2. And then for each of these, use proper probability notation, which means you're using the P in the parentheses to find the probability of each of these events happening. So the probability that a randomly selected mother has less than 2 children, well, less than 2 children would mean 1 child. So the probability of 1 child is 0.22. Make sure, again, you're using this notation for probabilities. Find the probability that a randomly selected mother has 1 or 2 children. So 1 or 2 children, I'm going to use that general addition rule that we talked about up here. So that would be A or B is A plus B. So it would be 1 or 2 would be 0.22 plus 0.41, which is 0.63. And the probability that a randomly selected mother does not have 4 or more children. So I said 4 plus children complement, so not 4 plus children, would be 1 minus the probability of 4 plus children. So 1 minus 0.3 is 0.87. So you can kind of think of it as if it's not 4 or more, that means it's 1, 2, or 3. So you could add up these to get the 0.87, or you could just do 1 minus this one to get the 0.87. Either way, you'll get the 0.87. So if there's any time left in class, you can use it to work on the textbook assignments. Otherwise, I will see you tomorrow.